So we had discussed that when material is being pulled, yeah, at its axis, length axis, or being pushed, then a stress sigma is applied, which is proportional to the force and inversely proportional to the area, the cross-sectional area. Then the strain will also occurs. Yeah, the shape will deform. Yeah, the material will deform, will be elongated when it is tensile size. It will be stretched at the same axis as the force. Then we express it as the dimensionless parameter strain, yeah, by dividing the elongation or the delta extension with the original line, yeah, L0. Then the connection between the sigma and epsilon is related through the Young's modulus or modulus of elasticity E. Okay, especially when the deformation still occurs in the linear elastic region. Yeah, when it is already in the plastic region, then we cannot use this Young's modulus or this Hooke's law equation anymore. Then the Poisson's ratio relates the tensile strain, the strain at the direction of the stress, with the lateral strain, yeah, the strain that occurs in the dimension perpendicular to the tensile strain. So the relationship that nu equals to the negative epsilon L divided by epsilon. So when the nu is large, it means that the material is easily deformed in the other axis, yeah, when the when a tensile stress is being given to that material. For example, here polymers has larger Poisson's ratio compared to ceramics and metals. So the unit of nu is also dimensionless, so it is dimensionless, so no unit. So here the graph shows the relationship between epsilon L and epsilon, but the gradient is negative. Yeah, the negative nu is the gradient between epsilon L, the lateral strains, versus the epsilon. When nu is above 0.50, density will increase. Yeah, it means that the epsilon L, the deformation at the perpendicular direction, is larger, yeah, or yeah, more than half of the deformation at the tensile direction. Okay. However, when it is less than 0.5, like these three materials, it means that the density decreases. Voids forms between the atoms in that material. So if we plot, yeah, when we have, remember the plot of the force versus separation in the atomic chapter about atomic binding, the slope of stress strain plot, which is proportional to the elastic modulus, depends on the bond strength of the metal. Okay, so when we have a very hard material, a very rigid material with high Young's modulus, usually then it occurs in strongly bonded metal. Yeah, when the gradient here at the force as a function of separation has higher gradient, like this, this red line. The second material here, represented by the blue line, is weakly bonded, and hence the Young's modulus will also be lower. Okay. Besides the nu and the epsilon, the E, the Young's modulus, and the Poisson's ratio, we have also other elastic properties. The elastic shear modulus, this shows the relationship between the tau and the gamma. The gamma is the shear strain, remember? When we put shear, the lower part surface is considered as fixed, the upper part is shifted, then it forms a an angle, yeah, the angle represented by this gamma. So this basically similar like strain, but the y-axis instead of sigma, it becomes the shear stress. So the graph of tau versus gamma here, when you draw when it is still in the elastic region, the gradient indicates the shear modulus, elastic shear modulus G. Then when Poisson ratio only relates the dimension length, the length change in the axis of in the direction of the tensile stress and its relationship with the perpendicular deformation, yeah. Then we also have another parameter called elastic bulk modulus. So this is related to the deformation of the material as a volume. Yeah, the elastic bulk modulus is called as K, is symbolized by K. Yeah, the P here represents pressure. So this is especially true for hydrostatic pressure. Yeah, hydrostatic pressure, or where the pressure comes from all direction. So the P is related to delta V over V0. So this is normalized again. So this is a dimensionless parameter also. And the gradient will be minus K. Yeah, because with increasing pressure, the volume should decrease, right? The delta V will decrease. When the pressure decreases, volume increases. That is why the gradient is negative. Okay. For isotropic material, what is isotropic material? Remember, isotropic materials usually when the crystalline, when it is polycrystalline, the crystalline grain is spherical, yeah? So it doesn't have any particular preference of orientation towards a certain direction, almost uniformly or oriented similarly towards all direction. For such material, yeah, which we call as isotropic, then the G, the shear modulus, is related with the Young's modulus with this equation. So the G equals to the E divided by 2 times 1 plus nu. And the elastic bulk modulus is related to the Young's modulus through this equation, E divided by 3 times 1 minus nu, minus 2 nu. So this graph can be seen in the textbook also. This is the comparison of several Young's modulus. So as we had discussed multiple times, yeah, due to its structural property, diamond has the highest Young's modulus. So it is considered as the hardest material on Earth. Yeah, that is why it is mostly used as the coating material for drill bit. After that, followed by silicon carbide. Yeah, so this is ceramics and something like that. Then metal alloys also have similar Young's modulus as this aluminum oxide, tungsten, molybdenum, and steel. Yeah, the softest among these metal alloys, yeah, the lowest Young's modulus is magnesium and tin. Yeah, if you know the soldering tin, which I believe you have used, yeah, soldering tin in the lab or maybe in your house, in your home, it's very easily breakable, easily deformable, yeah, very soft. But below that, even we have polymers, which normally has very low or very small Young's modulus, yeah, in the range of less than 10 gigapascal, okay, 4 gigapascal, something like that. Even some material has less than 1 gigapascal. Well, here, if we see, most metals have tens of gigapascal. And diamond could also have hundreds of gigapascal Young's modulus. Composites, on the other hand, has wider range of Young's modulus because their Young's modulus can be adjusted or can be tuned by adjusting the composition of the composite. Whether you are mixing, for example, polymer with metals or polymer with ceramics, and also what is the percentage of their width percentage. Yeah? It will determine the eventual material property, including the Young's modulus of that composite. These are some useful linear elastic relationship. Here we have in simple tension. So delta is basically, if we write down, yeah, this is how is this derived. Delta is basically epsilon times the L0, right? The initial length times the strain. So from here, we extend further that epsilon equals to sigma the stress divided by the Young's modulus. And then this is further expanded by expanding sigma. Sigma is the tensile stress equals to the force divided by the cross-sectional area. So this becomes this equation. Okay, the delta is the extension, yeah, of the, which is then divided by 2 because it occurs at both ends. Okay, so I cannot erase it. Okay, I can erase. So the lateral strain, on the other hand, then you just need to multiply this delta value with the with the Poisson ratio nu, and remember to put negative sign here. In torsion, the alpha, yeah, is the angle of the twist. Yeah. Here, in the circumference direction, not in the radial direction, can be calculated using this formula. 2 times the moment times the initial length divided by pi times the radius power 4 times the g. Yeah, the g is the modulus of the shear modulus. Yeah, the elastic shear modulus g. So material geometry, from here we know that material, geometric, and loading parameters all contribute to deflection. If we look here, the delta, the variable that contributes to its value is the force. The geometric condition of that material, the length and the cross-sectional area, as well as the material property E. So this is the loading, the force is the loading, E is the material property. The larger the elastic moduli, the smaller the elastic deflection. If you have larger E, yeah, in this, for example, the hard material with very large Young's modulus, then the resulted deflection, the elastic deformation will be small. Okay. Okay, all this formula occurs when the materials are being deformed in the linear elastic region. As we have also discussed in the one of the slides earlier, when we further deform, then the material will undergo plastic deformation, in which case then the deformation will be permanent. Okay, so at lower temperatures, which is defined as temperature lower than 1/3 of the melting temperature, looks like this. Yeah, when you further pull or push the material, then slip will occur between the crystalline plane. So then both elastic will also still occur, which is the increased space between this crystal between the atoms, but plastic deformation also occurs at larger stress. When the load is released, this deformation due to the slipping of the crystalline plane will still there. Yeah, it is irreversible. The distance between the plane here come back to original condition like this, but the slip still occurs. This is what causes permanent plastic deformation after the load is removed. Okay, and that strain, when it is being released, yeah, the permanent strain is called as the plastic strain. Okay, now we introduce another parameter called as another mechanical property called as yield strength. What is yield strength? This is the stress, yeah, at which noticeable plastic deformation has occurred. So here, please pay attention to this noticeable. So if it is not noticeable, then we don't really count it. The moment when during the measurement with measurement technique, with any measurement technique, we can see a noticeable plastic deformation. The strength, the stress that caused that permanent deformation is called as the yield strength, sigma y. Here. So, for example, when this one after the elastic region, it is being further deformed, maybe only until this region. Let's see. Let's give. Okay, where's the color? Let's see. For example, I only deform in halfway here. Why this is not yield strength? Because maybe when it is released, yeah, so the strain will be only here. Let's say maybe this is less than 0.001, yeah, etc. This is maybe too small to be noticeable by bare eye or by any conventional length measuring technique. So if that is the case, then it is not called as the yield strength. Yeah. However, when we further pull and pull until here, when the sigma is released, then it will still deform here, and this deformation can be noticed by bare eye. In this case, for example, the plastic deformation, the plastic strain is 0.002, yeah, or 0.2%. So in that case, this is the yield strength. For example, we have 2-inch length sample what is the deformation upon when it is at yield strength. So the epsilon is 0.002. Okay, then and this is equal to the delta z over z, the initial length. So the length, the deformation will be because z is 2 inch, right? The delta z will be 0.004 inch. Okay, so please remember that again, that this word noticeable. So this is defined now when epsilon p, the plastic strain, equals to 0.002. Okay, so let's see, compare this sum of the yield strength of some materials. As we can see that yield strength is different than elasticity, elastic modulus, yeah, Young's modulus. Even when material has high Young's modulus, means high, the slope is very high, like in ceramics, most ceramics. It doesn't matter that they will have also high yield strength. Yeah, with ceramics, for example, they cannot deform in the plastic region. Okay, very difficult to deform in the plastic region. They can deform in the elastic region, but the moment you surpass certain stress, for ceramics, they will usually just break. Okay, that is why it's hard to measure, since in tension, fracture usually occurs before yield. Okay, remember the meaning of the word yield in English. The yield means to surrender, to follow the direction of the force, to follow in this case the direction of the stress. So with metal, usually they are yieldable. Yeah, that's like it. When they put force or stress in this case above this value, above the beyond the elastic region, they will deform. This is, in this case, then they will have plastic deformation. Ceramics, on the other hand, the value, the Young's modulus may be larger. It means they have steeper slope. However, afterwards, after certain threshold, they will just break. You cannot make them yield. With ceramics, you cannot make them yield. That is why it just break. Metal alloys, on the other hand, is deformable. They are formable. We call it as ductile. This property is ductile. Later we will see another parameter called as ductility. The opposite of ductile is called as fragile, which is the characteristic of graphite, ceramic, or semiconductor. That's why with glass, for example, you have glass in your home, the ceramic or ceramics. You try to put force on it, or pull. It can withstand it, or maybe very tiny deformation which you cannot see with bare eye. After you push or you pull that ceramic glass, whatever, above certain value, it will just break. It cannot bend, it cannot deform. On the other hand, you have spoon, right? Metal spoon or metal fork. You can still bend, right? You can still bend it. You can still maybe stretch it if you have enough strength. It will deform after you bend, after you stretch above certain stress value. It cannot deform. It cannot go back to its original shape and size. It means that for metal, they can have plastic deformation. So here we see metals, most of them have yield strength in the megapascal region, sigma y. Graphite, ceramics, semiconductor, they do not have. They just break. Above certain value, they will just break. Polymer has yield strength, but at much lower value compared to metal. That's why the polymer can be easily deformed with plastic deformation. It's also why they are popularly called as plastic, because they can easily have plastic deformation. Composites or fibers is very hard to measure, because in tension, the fracture usually occurs before yield. So this is a similar property like graphite. So here you see the data. There is this what do you call it? Superscript, letter that indicates the process how they are being made. So for example, even for steel, when the steel is annealed compared to cold drawn, then the steel with annealed steel will have higher yield strength. So it means it is more difficult to deform compared to the steel which is cold drawn. What does it mean? Anneal means you put it for these are the processing parameters. Anneal means you put further in high temperature. Cold drawn is being cooled, being being from molten state into solid state in cold temperature, something like that, etc., etc. Another mechanical parameter is tensile strength. Okay, still using the same sigma over epsilon graph. So this is the elastic region. Then after this elastic region, when you pull further the specimen, especially for metal, it will start to yield. This is the region where it has plastic deformation. You pull further, it will deform, which if you unload the stress, it cannot go back to its original state, because plastic deformation already occurs. However, if you pull further, pull until certain point here, it will just start to break. Why this graph decrease? So it means if you pull further, the stress does not build up anymore. Instead, it will start to decrease until here the specimen breaks. That this deformation is when necking starts to occur at the middle of the specimen. Then it starts to break. The tensile strength is the value of this peak engineering stress here, yeah, where the specimen starts to have necking phenomena here. Yeah, because here when you deform further, the stress got smaller. So when this one, after this, it starts to fracture and then breaks, the graph stop. It doesn't continue. So this is what we call as ultimate strength. So the peak of this graph is called tensile strength, while this one, where it breaks and no more can be measured because now the connection is just gone between the upper part and lower part. It just break in the middle. Then that stress where it occurs is called as ultimate strength. The next XS stress concentrator. So in metals, this tensile strength is where noticeable necking starts. Necking here is when the middle cross-sectional area of the specimen starts to decrease compared to the other parts of the specimen. In polymers, it occurs when polymer backbone chains are aligned and just about to break in the tensile strength. This is the comparison of tensile strength for various material. Since the ceramics, yeah, see here as you see, metal alloys have relatively higher tensile strength compared to the other. Graphics of ceramic semiconductor here, because they mostly they are fragile, they cannot deform. They do not have yield strength. So their tensile strength even are smaller than many of the metals. So how to interpret this? It means when you pull and pull and pull ceramics, yeah, or graphite or semiconductor beyond its linear elastic region, then only for a while it will immediately break. It does not deform in the plastic region. It just breaks. That's why the tensile strength is smaller than many of the metals. Ceramic polymers, on the other hand, also have smaller tensile strength compared to ceramics and metals. Yeah, for polymer. Composite fiber, as expected, they could have a wide range of value of tensile strength because this property, this mechanical characteristic will depend on the composition of that composite. Okay, I've mentioned the word ductile. What does it mean with ductile? Ductile means, in layman term, it can be said that when a material is formable, it can be deformable, and then stay in that form. Usually, this material in our engineering world is the metal. Yeah, that is why, since metal has very high ductility, it can be deformed to make various shape. We can make metal to become car, to become spoon, to become airplane, etc. The ductility is defined mathematically as the percent elongation, EL here elongation, equals to LF minus L0 divided by L0 times 100%. Okay. So, for example, with a ductile material like most metals, after the elastic region, then it will reach the yield strength here, somewhere here, then it will reach the tensile strength, ultimate at the tensile at the peak of the curve, then immediately to fracture, to fracture or ultimate strength. Yeah. The tensile strength, then this here fracture ultimate strength where it just breaks. On the other hand, with material which is very rigid like semiconductor or ceramics, they have longer elastic region because they are very difficult to deform. They may deform a little bit, but afterwards they do not have this kind of longer curve, but instead they just break from the ultimate tensile strength. This one from the TS, the tensile strength, it also becomes the ultimate strength. when it just breaks. So ductility is deformed as the percentage of elongation, the final length minus the original length divided by the original length. So for example, like this, when we put tensile strength, tensile stress at its two ends, yeah, pulling it, then making a course. Okay, this final length, then this is permanent deformation. It cannot go back to this original condition because it is already beyond the linear elastic region. So the difference between the final length and the original length divided by the original length, and then we times 100 to take the percentage. This is the definition of ductility. So a material which has high ductility, it means that they can be deformed at larger value compared to material which has low ductility. Low ductility, we can say it that the material is fragile. Fragility is the opposite of ductility. Besides from the length, the ductility can be also measured from the cross-sectional area. A0 minus A final divided by A0 times 100. Then we know what toughness. Toughness is another material mechanical property. This is defined as the energy to break a unit volume of material. It can be approximated by the area under the stress strain curve. Okay, we have the stress strain curve. You see here that even though ceramics is considered hard because of its very high Young's modulus, but because it doesn't have yield strength, it doesn't have ultimate tensile strength, it doesn't have tensile strength, it doesn't have ultimate strength, we can call that it has small toughness because it breaks easily. Metal, on the other hand, they can be deformed before they break here. So the area underneath it is quite big. That's why metal, we can consider them to have large toughness. Plastic, on the other hand, or polymer, unreinforced polymer here, low Young's modulus, small Young's modulus, then it doesn't have ultimate strength also. It's very long. Like this. The area underneath this still below this metal. So they have very small toughness. Sorry, not fragile, but brittle. Yeah? The opposite of ductility is brittleness. Just remind it here. So the opposite of ductility is brittleness. The adjective is ductile and versus brittle. Okay. So ceramics like glasses, yeah, or semiconductors are considered as brittle material because they do not have plastic energy underneath their stress strain curve. They just break here. Although they have very high Young's modulus, the slope is very high. Metals, on the other hand, because they have a lot of area underneath their curve, they are ductile. They are very tough. They are tough. Yeah. So in brittle fracture, in brittle material like this, they only have elastic energy. That is why immediately when it goes beyond the elastic region, it will just break. With ductile material like metals, since there is also plastic energy underneath this after the yield strength, and they are considered as tough, as large toughness. Then another mechanical property called as resilience, UR. This is the ability of a material to store energy. Energy stored best in the elastic region here. So the UR, yeah, the area under it, under the stress strain curve, basically, is considered as the energy. Integral from 0 until epsilon y. Yeah, the epsilon y here when the plastic deformation, yeah, when the noticeable plastic deformation. If you assume a linear stress strain curve, this will simplify to half sigma y times epsilon y. And the resilience is a function of the yield strength and yield strain. Then we have what we call as elastic strain recovery. When we have load, then it start to have yield when the loading is above the yield strength. Then after that, when the loading is released or unloaded, it goes to not really original condition, but because many of it still has some plastic deformation. Now, the difference between this value of the plastic strain with the strain that it should have at the D here is the peak. The ultimate, the tensile strength here, and the tensile strength is when we draw vertical line, this difference is the elastic strain recovery. Okay. So when you apply load, when you reapply load, it will increase again this in the elastic region. After the elastic strain is surpassed, it will undergo plastic deformation. So ceramic materials are more brittle than metals. Why is this so? Yeah. In the previous example, ceramic material does not have tensile strength. It just break in the ultimate strength. Yeah, after the no yield strength, no yield stress. Because in crystalline, most of the ceramic materials are crystalline. Sorry, most of the metals crystalline. The deformation occurs through the dislocation, the motion of the dislocation. This dislocation could be in the form of vacancy or interstitial. But in ceramics, which is highly ionic solid, the dislocation of motion is difficult because there is only few slip system. Yeah, in ceramics. The resistance to motion of ions like charge anions past one another is also quite high because of the ionic nature of many ceramics. But in metals, since they have metallic bonding with electron cloud, it is still quite easy, so they can deform easily. So how to characterize the material such that we can get all these mechanical properties here? Of course, we have explained the tensile test machine. There is also flexural test to measure the elastic modulus. So room T behavior is usually elastic with brittle failure. We can use 3-point bending testing because if you pull for brittle material like ceramic, you cannot pull it too much when it is above the when it is beyond elastic region, it will just break. So then how to measure the elastic modulus? Also with ceramics, because the Young's modulus, the elasticity modulus is very high, the deformation is very small. Yeah, even we apply very large force, the tensile strength is very small and hardly noticeable or very difficult to measure. So what we can do is using 3-point bending like this, instead of axial stress and axial strain. Axials mean in the direction of the length. We can apply, instead of that, we can apply flexural stress, where we bend the material. The force is put in the middle to bend the material. The material is being held at 2 points here, which is located L/2. And the deflection at the middle compared to that this point will be called as midpoint deflection. Then this is the midpoint deflection is related with the F and the L can be related to calculate the Young's modulus. So the function of F over delta, the slope, and if we see the slope, equals to this L cubic for rectangular cross section divided by 4 times B times D. B is the width, D is the height. If it were circular, then the Young's modulus here, F over delta, is like this: L cubic divided by 12 pi r power 4. Okay, so by measuring the delta in the flexural binding test, 3-point binding test, 3-point bending test, you measure this delta from the middle point to the edge. You know that, then you measure the force. You obtain this as the gradient, and you obtain. So this is the gradient, yeah. So this is F over delta is the parameter here. The gradient will be this one. Oh, the slope is the F over delta, yeah. And times the dimensions, you can obtain the Young's modulus of that ceramics or the hard material. To measure flexural tests, yeah, we can use also 3-point bending to measure room, the flexural strength, yeah, the strength just before it formed. So here in the location of maximum tension, the flexural strength sigma fx equal to 3fl, the length, divided 2bd square. This is if rectangular cross section. If it is circular cross section, divided by pi r cubic. Yeah, the flexural force times the length. Typical value is, as can be expected, for silicon nitride and silicon carbide, which is considered very hard material. They have very big sigma fx flexural strength. Yeah? But the Young's modulus is also big, yeah, but not as big aluminum oxide here. Glass soda or slime, which is ceramic, basically has a small flexural strength, so that's why it breaks easily. For polymer, yeah, we have brittle polymer, which has similar characteristics, properties like glass or ceramics. We have plastic polymer, which has properties similar to metals. We have also polymer, which can be classified as elastomer. This elastomer, it doesn't break, it just elongates. Yeah, with strain, it elongates quite big, yeah, and without considerable significant change of the stress. So the fracture strength of polymer is more or less 10% of those for metal. And for this polymer, deformation strength for polymer is larger than 1000%. For this one, yeah, larger than 1000%. It can deform means 10 times. The strain is 10. For most metals, deformation strain is less than 10%. Temperature and strain rate can also influence. Yeah? For example, here in polymer, for thermoplastic polymer, when you decrease the temperature, then the Young's modulus will increase. The tensile strength will also increase. However, the ductility will decrease. Okay, the percent elongation will increase when temperature is decreased here, so in this region. But so the vice versa is also correct. So when you increase the temperature, then you start to have plastic deformation region. Okay, then you will have also the this one is the TS, tensile strength. You have also you can also have the ultimate strength. Increasing the strain rate will have same effects as decreasing the temperature. Okay, so this is how we can modify the mechanical property of material based on its processing parameter. In this case, this is using adjusting the temperature as well as the strain rate. In stress relaxation test, strain intention to epsilon 0 and hold. Here, observe the decrease with stress in time, like this one. This is called stress relaxation time. Then the relaxation modulus epsilon RT can be calculated from sigma T. The stress itself divided by the epsilon 0, the strain, the tensile strain. There's a large decrease in ER, the relaxation modulus for temperature larger than the glass transition temperature, the TG. Right? This is for polymers. So polystyrene, polycarbonate has very high TG, the glass temperature, glass transformation temperature values. While polyethylene, low density, LDPE or high DPE, has negative temperature for its glass transition. Okay, let's have a break for a while because of the time. Let's continue again. So this now previously was this one, yeah, the influence in thermoplastic, yeah, in thermoplastic polymer, when we decrease the temperature, it will increase the Young's modulus, increase the tensile strength, and decrease the ductility. The sustained elongation here is ductility. While we increasing the strain rate will decrease the same effect as decreasing this temperature. Okay. There's also time-dependent deformation. So it means that depending on the time, what we call a stress relaxation test, the strain intention to epsilon 0, and we hold it. However, the stress will not be the same. Normally, if it is time-independent deformation, the normal deformation, when we stretch, the stress will remain the same. However, in some material, we can observe this decrease of stress with time. Okay? This is called as the relaxation modulus. The ERT equals to the sigma as a function of time divided by the epsilon 0. When the temperature of the material is above the glass transformation temperature, yeah, the transition region, TG, then there will be a large decrease of this relaxation modulus. Yeah, right. This is the transition region. For temperature larger than TG, for example, this TG is here, yeah, and TG is above, the temperature of the process is above this. So here the ER will immediately decrease. Yeah. So what does it mean? What it means like this. Yeah, it will decrease more significantly compared to if the temperature is smaller than the glass transformation temperature. This is for polymer also. Okay. This is the representative of the glass transformation temperature values for several polymers. Then the hardness. So as we discuss these parameters, remember that then maybe until now you consider some of this terminology similar or the same. Yeah, toughness, hardness, strength. But as you can see now, each of these words has its own definition, which may represent different physical concept. So the hardness is itself is mostly more towards its surface parameter. Yeah, the hardness of a material is the material's resistance to permanently indenting the surface. So when a material has large hardness, it means that it has resistance to plastic deformation or cracking in compression, because hardness is measured by compressing the material by other harder material, until it deform. When the deformation is small, it means that that material has high hardness or large hardness. Large hardness means also better wear properties. Wear properties is related when the materials are in friction to other surface of material. Okay. For example, like in drill, I give many times the example of drill bit or saw. Yeah. In drill bit or saw, the material has to be in friction, yeah, so that then it can drill, and the material of being drilled will be uh, released, yeah, so that a hole is made. Similarly, when we are sewing, yeah, cutting with a saw, the saw has to be in friction with the material being cut, yeah, until the formation occurs and then it is being cut. But when the material is, that is why usually then the material being used as the saw eye or the saw tip or the drill bit has to be very hard. Yeah. Hard here is in this sense of parameter, yeah, the hardness parameter, because it has to have very good wear properties. It doesn't wear even though you are putting it in friction with other materials. And on the other hand, the other material will, because it has less hardness compared to the saw, the saw, the saw material or the drill bit, then it will be worn and then cut easily. So how to measure hardness? Usually we have this material being used to compress the material being in test. Yeah, here we apply force. That material will have certain diameter. For example, here 10 millimeter sphere. After that material is being removed, then we measure the indentation caused by this load, yeah, this loading in the tested material. If the tested material has smaller indents, it means it has larger hardness. Most plastic has small hardness, yeah? With here the diamond being the hardest of all. After diamond is the treated steels and the cutting tools. Why you have the diamond cutter, yeah, to cut glass. Glass itself is already quite hard, yeah, because it is made from ceramics. But diamond is harder. And you can cut to, if you want to make smaller pieces of glass. The unit or the measurement of hardness can be measured in Rockwell scale or HB, the Brinell hardness scale. Using Rockwell, there will be no major sample damage. Each scale runs to 150, but only useful in range 20 to 100. You can put a minor load of 10 kilogram. If you have a diamond as the load material, then you put maybe as the major load only up to 60 kilogram. But if it is 1/16 inch ball, up to 100 kilogram. Now diamond with major load could be up to 150 kilogram. The Brinell hardness, yeah, is related to the tensile strength. Yeah. So the tensile strength is measured in PSIA, then it is 500 times the Brinell hardness. If it is in megapascal, then 3.45 times the Brinell hardness. So this is the shape, yeah, of the loading material. If it is in Brinell, it uses this 10 millimeter sphere of steel or tungsten carbide, like this, yeah, to do the loading. And after that, when the loading of the force is released, we measure the indentation. The Brinell hardness is measured from this. The P represents the pressure, the applied load in kilogram, while D here is the diameter. The large D is the diameter. The small d is the indentation towards the depth of the material. Thicker micro harness uses diamond pyramid like this, with an angle of the tip of 136 degrees. And from cross section, it looks like a pyramid, yeah, with D1 and D2, D1 parameter here. The indentation from top view. If we put load a P, then the thicker micro hardness can be calculated as HV equals to 1.854 times P divided by D square. Dope micro hardness measured using diamond pyramid as well, similar like thicker, but has different dimension. It has this T. It is not square diamond pyramid, but instead more of different rectangle, or elliptical, yeah, because the axes have different dimension. Then we have Rockwell and superficial Rockwell, like this, yeah, in the form of diamond cone. Yeah, this is the load as we have mentioned earlier: 60 kilogram, 100 kilogram, and 150 kilogram. Okay. There's also another mechanical property called as true stress and strain. True stress sigma T is measured from the force divided by the cross-sectional area. True strain is measured as the natural logarithm of Li divided by Lo, the length. Yeah. Here, the connection between true stress and the epsilon and the stress is calculated from this formula: sigma T equals to sigma times 1 plus epsilon. The relationship between true strain and the engineering strain is through this natural logarithm of also epsilon T equals to natural logarithm of 1 plus epsilon. So in engineering means in real experiment, usually for metal, it will look like this in the blue line. But the true strain is when it doesn't break, yeah, it will grow, increase, and increase. This is due to surface area changes when sample is being stretched. Okay. The I here represents the initial, yeah, the instant surface area when the sample is being stretched. Okay, some of the mechanical properties can be changed by specific processing. Yeah, of course, we will learn this in another chapter later, to know how specific processing can alter or can adjust the mechanical property of the material. But let's say here now one of the process is called as hardening, when we try to harden the material. Physically speaking, or from material science perspective, is when the yield strength increase due to plastic deformation. By making the material to deform permanently or plastic, then there will be an increase in sigma y. When we have large hardening like this, the sigma y increases from sigma y0 to sigma y1. Yeah, so it will have larger noticeable plastic strain. With small hardening, however, yeah, the yield strength is smaller. When we curve fit the stress strain response, the true stress sigma T will be equals to K times the true strain power to N. This is the hardening exponent. With N equals to 0.15 for steel, some steel, and equal to 0.5 for some copper. Yeah, so material properties often vary between one material to another material. So elastic modulus material property, critical properties depend largely on sample flaws, like whether there are defects or not. Yeah, again, as we have learned in the previous chapter, the defects define or determine the properties of the material, not only mechanical but also other properties, including electronic and many other. So sometimes you have to collect large sample to take into account the sample variability. And then use statistic mean or standard deviation to express that material properties. And since every material has yield strength, and when you are designing biomedical device or biomedical or implant, then you know you can calculate the stress that implant, for example, or the device has to endure during its operation. So in order that no complications arises, you should try to design such that working stress condition should be well below the yield strength limit of that material. So this is expressed in the factor of safety N. Usually it is between 1.2 and 4. For example, calculate a diameter D to ensure that yield does not occur in this 1045 carbon steel below. So it means it will not deform plastically or permanently. If we use the factor of safety 5, L0 is given. So the type is given, that 11045 plain carbon steel. Yield strength is known, 310 megapascal. Tensile strength is known, 565 megapascal. It is being pulled by 220,000 Newton. Now the question is, what is the diameter? If the factor of safety is 5, yeah, the sigma working is 220,000. Sorry, the yield strength is 310 megapascal. Then the sigma working is 310 divided by 5. Yeah? And this should be that will be the limit. So the sigma working should be equals from this 220,000 divided by the cross-sectional area, pi times d square over 4. So from here, so 310 divided by 5, we obtain the sigma working, and the sigma working equals to this force divided by the cross-sectional area. So from here, then we can calculate the cross diameter of the rod, yeah, which is 6.7 centimeter. Okay, as a summary, then these are size independent measures of load and displacement, respectively. Stress strain, yeah. Elastic behavior is reversible behavior shown as linear relation between stress and strain. To minimize deformation, select a material with a large elastic modulus E or G. Plastic behavior, when it goes beyond this elastic linear region, when the material starts to deform, shown by this deformation in the curve. So when you release the loading, it cannot go back to the original 0 position, but instead it will have this plastic deformation, plastic strain, epsilon P. Then it occurs when the tensile or compressive uniaxial stress reaches the yield strength. Toughness is a measure of the energy needed to break a unit volume of material. And we see that ceramics usually has smaller toughness compared to metal. Ductility is the plastic strain at failure, or in layman term, we can say that ductility is how formable a material is. And metal usually they are easily formed, that's why they are called as ductile. While glasses or ceramics they are the least ductile, we call them as brittle. Brittle is the opposite of ductile. Okay, so that will be all for this chapter on mechanical properties. Let's have some exercise. Yeah, as usual.